A set of vectors in a vector space V is called a basis, or a set of basis vectors, if the vectors are linearly independent and every vector in the vector space is a linear combination of this set. In more general terms, a basis is a linearly independent spanning set. Given a basis of a vector space V, every element of V can be expressed uniquely as a linear combination of basis vectors, whose coefficients are referred to as vector coordinates or components. A vector space can have several distinct sets of basis vectors, however each such set has the same number of elements, with this number being the dimension of the vector space. Definition: a basis B of a vector space V over a field F is a linearly independent subset of V that spans V. In more detail, suppose that B equals V1, Vn is a finite subset of a vector space V over a field F. Then B is a basis if it satisfies the following conditions. The linear independence property. For all A1 and F, if A1 V1 plus A and Vn equals 0, then necessarily A1 equals n equals 0, and the spanning property. For every x in V it is possible to choose A1 and F such that x equals A1 V1 plus A and Vn. The numbers I are called the coordinates of the vector x with respect to the basis B, and by the first property they are uniquely determined. A vector space that has a finite basis is called finite-dimensional. To deal with infinite-dimensional spaces, we must generalize the above definition to include infinite basis sets. We therefore say that a set BV is a basis, if every finite subset BO obeys the independence property shown above, and for every x in V it is possible to choose A1 and F and V1, Vn be such that x equals A1 V1 plus A and Vn. The sums in the above definition are all finite because without additional structure the axioms of a vector space do not permit us to meaningfully speak about an infinite sum of vectors. Settings that permit infinite linear combinations allow alternative definitions of the basis concept. See related notions below. It is often convenient to list the basis vectors in a specific order, for example, when considering the transformation matrix of a linear map with respect to O basis. We then speak of an ordered basis, which we define to be a sequence of linearly independent vectors that span V. See ordered bases and coordinates below. Properties. Again, B denotes a subset of a vector space V. Then, B is a basis if and only if any of the following equivalent conditions are met. B is a minimal generating set of E, i.e., it is a generating set and no proper subset of B is also a generating set. B is a maximal set of linearly independent vectors, i.e., it is a linearly independent set but no other linearly independent set contains it as a proper subset. Every vector in V can be expressed as a linear combination of vectors in B in a unique way. If the basis is ordered, then the coefficients in this linear combination provide coordinates of the vector relative to the basis. Every vector space has a basis. The proof of this requires the axiom of choice. All bases of a vector space have the same cardinality, called the dimension of the vector space. This result is known as the dimension theorem, and requires the ultrafilter lemma, a strictly weaker form of the axiom of choice. Also, many vector sets can be attributed a standard basis which comprises both spanning and linearly independent vectors. Standard bases, for example, in Rn, E1, n, where A is the ith column of the identity matrix. In P2, where P2 is the set of all polynomials of degree at most 2, 1, x, x2 is the standard basis. In M22, M1, 1, M1, 2, M2, 1, M2, 2, where M22 is the set of all 2 times 2 matrices, and n is the 2 times 2 matrix with a 1 in the m, n position and zeros everywhere else. Change of basis. Given a vector space V over a field F, and suppose that V1, Vn, and alpha1, alpha-n are two bases for V. By definition, if she is a vector in V, then she equals x1 alpha1 plus xn alpha-n for a unique choice of scalars x1, xn in F called the coordinates of she relative to the ordered basis alpha1, alpha-n. The vector x equals in Fn is called the coordinate tuple of she. The unique linear map phi Fnv with phi equals alpha j for j equals 1, n is called the coordinate isomorphism for V and the basis alpha1, alpha-n. Thus phi equals she if and only if she equals x1 alpha1 plus xn alpha-n. A set of vectors can be represented by a matrix of which each column consists of the components of the corresponding vector of the set. As a basis is a set of vectors, a basis can be given by a matrix of this kind. The change of basis of any object of the space is related to this matrix. For example, coordinate tuples change with its inverse. Examples: consider R2, the vector space of all coordinates where both A and B are real numbers. Then a very natural and simple basis is simply the vectors E1 equals and E2 equals. Suppose that V equals is a vector in R2, then V equals A plus B. But any two linearly independent vectors, like n, will also form a basis of R2. More generally, the vectors E1, E2, n are linearly independent and generate Rn. Therefore, they form a basis for Rn and the dimension of Rn is n. This basis is called the standard basis. Let V be the real vector space generated by the functions a and e2t. These two functions are linearly independent, so they form a basis for V. Let Rx denote the vector space of real polynomials, then is a basis of Rx. The dimension of Rx is therefore equal to Lf0. Extending to O basis. Let S be a subset of a vector space V. To extend S to a basis means to find a basis B that contains S as a subset. This can be done if and only if S is linearly independent. Almost always, there is more than one such B, except in rather special circumstances. A similar question is when does a subset S contain a basis? This occurs if and only if S spans V. In this case, S will usually contain several different bases. Example of alternative proofs. Often, a mathematical result can be proven in more than one way. Here, using three different proofs, we show that the vectors n form a basis for R2. From the definition of basis we have to prove that these two vectors are linearly independent and that they generate R2. Part 1. Then, and in subtracting the first equation from the second, we obtain. So adding this equation to the first equation then. Hence we have linear independence. Part 2. To prove that these two vectors generate R2, we have to let be an arbitrary element of R2, and show that there exist numbers R, S are such that. Then we have to solve the equations. Subtracting the first equation from the second, we get. And then and finally by the dimension theorem, since is clearly not a multiple of and since is not the zero vector, these two vectors are linearly independent. Since the dimension of R2 is 2, the two vectors already form a basis of R2 without needing any extension. By the invertible matrix theorem, simply compute the determinant. Since the above matrix has a non-zero determinant, its columns form a basis of R2. C. Invertible matrix. Ordered bases and coordinates. A basis is just a linearly independent set of vectors with or without a given ordering. For many purposes it is convenient to work with an ordered basis. For example, when working with a coordinate representation of a vector, it is customary to speak of the first or second coordinate, which makes sense only if an ordering is specified for the basis. For finite-dimensional vector spaces, one typically indexes a basis phi by the first n integers. An ordered basis is also called the frame. Suppose V is an n-dimensional vector space over a field F. A choice of an ordered basis for V is equivalent to a choice of a linear isomorphism phi from the coordinate space Fn to V. Proof. The proof makes use of the fact that the standard basis of Fn is an ordered basis. Suppose first that phi Fnv is a linear isomorphism. Define an ordered basis phi for V by equals phi for 1 in where A is the standard basis for Fn. Conversely, given an ordered basis, consider the map defined by phi equals x1 v1 plus x2 v2 plus xn vn, where x equals x1 e1 plus x2 e2 plus xn en is an element of Fn. It is not hard to check that phi is a linear isomorphism. These two constructions are clearly inverse to each other. Thus ordered bases for V are in one-to-one correspondence with linear isomorphisms Fnv. The inverse of the linear isomorphism phi determined by an ordered basis phi equips V with coordinates. If, for a vector v phi minus 1 equals Fn, then the components aj equals aj are the coordinates of V in the sense that V equals a1 v1 plus a2 v2 plus and vn. The maps sending a vector v to the components aj are linear maps from V to F because of phi minus 1 is linear, hence they are linear functionals. They form a basis for the dual space of V, called the dual basis. Related notions. Analysis in the context of infinite-dimensional vector spaces over the real or complex numbers. The term Hamel basis or algebraic basis can be used to refer to a basis as defined in this article. This is to make a distinction with other notions of basis that exist when infinite-dimensional vector spaces are endowed with extra structure. The most important alternatives are orthogonal bases on Hilbert spaces, Schauder bases and Markovitch bases on normed linear spaces. The term Hamel basis is also commonly used to mean a basis for the real numbers R as a vector space over the field Q of rational numbers. The common feature of the other notions is that they permit the taking of infinite linear combinations of the basis vectors in order to generate the space. This, of course, requires that infinite sums are meaningfully defined on these spaces. As is the case for topological vector spaces, a large class of vector spaces including e.g. Hilbert spaces, Banach spaces or Frechet spaces. The preference of other types of bases for infinite-dimensional spaces is justified by the fact that the Hamel basis becomes too big in Banach spaces. If X is an infinite-dimensional normed vector space which is complete, then any Hamel basis of X is necessarily uncountable. This is a consequence of the bare category theorem. The completeness as well as infinite dimension are crucial assumptions in the previous claim. Consider the space of the sequences of real numbers which have only finitely many non-zero elements, with the norm its standard basis, consisting of the sequences having only one non-zero element, which is equal to 1, is a countable Hamel basis. Example: in the study of Fourier series, one learns that the functions 1, sin, cos, n equals 1, 2, 3, are an orthogonal basis of the vector space of all functions on the interval 0, 2 pi, that are square integrable on this interval, i.e., functions f satisfying the functions 1, sin, cos, n equals 1, 2, 3, are linearly independent, and every function f that is square integrable on 0, 2 pi is an infinite linear combination of them, in the sense that for suitable coefficients ac bk. But many square integrable functions cannot be represented as finite linear combinations of these basis functions, which therefore do not comprise a Hamel basis. Every Hamel basis of this space is much bigger than this merely countably infinite set of functions. Hamel bases of spaces of this kind are typically not useful, whereas orthonormal bases of these spaces are essential in Fourier analysis. Geometry: the geometric notions of and affine space, projective space, convex set, and cone have related notions of beta. An affine basis for an n-dimensional affine space is points in general linear position. A projective basis is points in general position in a projective space of dimension n. A convex basis of a polytope is the set of the vertices of its convex hull. A cone basis consists of one point by edge of a polygonal cone. See also a Hilbert basis. Proof that every vector space has a basis. Let V be any vector space over some field F. Every vector space must contain at least one element, the zero vector 0. Note that if V equals 0, then the empty set is a basis for V. Now we consider the case where V contains at least one non-zero element, say V. Define a set X as all linear independent subsets of V. Note that since V contains the non-zero element V, the singleton subset L equals V. A V is necessarily linearly independent. Hence the set X contains at least the subset L equals V, and so X is non-empty. We let X be partially ordered by inclusion. If L1 and L2 belong to X, we say that L1 L2 when L1 L2. It is easy to check that satisfies the definition of a partially ordered set. We now note that if Y is a subset of X that is totally ordered by, then the union Li of all the elements of Y is an upper bound for Y. To show this, it is necessary to verify both that A, Li belong to X, and that B, every element L of Y satisfies L Li. Both A and B are easy to check. Now we apply Zorn's lemma, which asserts that, because X is non-empty, and every totally ordered subset of the partially ordered set has an upper bound, it follows that X has a maximal element. Finally we claim that Lmax is a basis for V. Since Lmax belong to X, we already know that Lmax is a linearly independent subset of V. Now suppose Lmax does not span V. Then there exists some vector W of V that cannot be expressed as a linearly combination of elements of Lmax. Note that such a vector W cannot be an element of Lmax. Now consider the subset LW of V defined by LW equals Lmax W. It is easy to see that A Lmax LW, and that B Lmax LW. But the combination of A and B above contradict the fact that Lmax is a maximal element of X, which we have already proved. This contradiction shows that the assumption that Lmax does not span V was not true. Hence Lmax does span V. Since we also know that Lmax is linearly independent over the field F, this verifies that Lmax is a basis for V, which proves that the arbitrary vector space V has a basis. Note: this proof relies on Zorn's lemma, which is logically equivalent to the axiom of choice. It turns out that, conversely, the assumption that every vector space has a basis can be used to prove the axiom of choice. Thus the two assertions are logically equivalent.